So welcome back, everybody, and to a new topic. And the topic this week is about quantum machine learning. This is a follow-up of the topic which we discussed last week. And today we are going to look at quantum neural networks, and we are going to try to link this with what we have seen before with the QAOA algorithm, and also with the variational quantum eigensolver. So the keyword for quantum machine learning, the existing methods, is that you can think of these as a variational quantum circuit, or normally what we also call a parameterized quantum circuit. This means that we are going to translate the input into qubits, and then we are going to perform operations with the rotations and adding C0 and other types of 2-qubit gates, which then entangle. And the parameters we get are going to be pretty similar to what we had with the variational quantum eigensolver in Project 1. This is also why we call these parameterized quantum circuits. Actually, the QAOA algorithm from last week is something which you can also view as a parameterized quantum circuit. Actually, it's normally called a variational quantum circuit. And the optimization is then done by classical algorithms. So we normally call this for hybrid algorithms. Now, there is one thing I just wanted to say is that I was actually in doubt whether I should keep something on quantum support vector machines. So when I've been teaching this topic on quantum machine learning, I often start with the support vector machines, the classical ones. And that often functions as a nice intermediate step towards quantum neural networks. So this year, since I find this topic with support vector machines a little bit boring, I wanted to jump into quantum neural networks. Actually, we replaced quantum support vector machines with quantum approximate optimization algorithm last week, which is another algorithm which is widely popular. So I'm not sure if I'm doing the right thing. So let's see what happens. But one of the things which I wanted to today is also to give you a reminder of what we had last week. So I wanted to bring back a little bit that, because that links well with this discussion on parameterized quantum circuits and variational quantum circuits. And then next week, we're also going to look more into some pretty nitty details of quantum neural networks. So today I wanted more to give you the main framework. There are also code examples where we compare classical neural networks. So we need to remind ourselves a little bit about classical neural networks. And next week, what I wanted to is to look at quantum neural networks applied to the solution of differential equations. And that leads us to quantum pins. That means quantum physics-informed neural networks. And for those of you who have been looking at these topics with solving differential equations with neural networks, this could be a topic which could be of interest. Then the final topic which we will cover is the so-called quantum machine learning with Boltzmann machines. And that will most likely be the last topic we cover this semester. So this is roughly about the structure for this week. But what I want to do is actually to bring up the slides from last week. So let's just take out this one and bring up the previous slides and remind ourselves a little bit of what we discussed last week. Actually, the recording is not yet available, but the notes here hopefully contain enough information so that you can actually encode yourself. And keep in mind also that the Jupyter notebooks, they are different from the PDF files. So the PDF files contains most of the mathematics, but basically no codes. And the codes for the QAOA from last week has examples with both the so-called max-cut case, but also applications to financial data. So if you're interested in looking at that, I mean, and as relevant for project number 2, if you want to look at applications to financial data, please feel free to use the codes. Keep in mind another thing, and I actually wanted to stress this, because when we looked at the answers to Project One, there were actually quite many of you who had not calculated the expectation values using the number of shots. So there were several of you who actually simply implemented a standard gradient descent method, like those which you will find in NumPy, in the SciPy library. But that was not the way we wanted it to be done in Project One, because it was explicitly stated, and this is also the reason for why some of you got a subtraction of points in Project One. Now, for Project Two, on the other hand, we are actually going to be less rigid when it comes to using the number of shots, the way you would simulate this on a quantum computer. And then you can actually use standard optimization algorithms. So that means that you, in a certain way, you would run the algorithms as a classical algorithm in a classical computer, but where you have rewritten all the operations as if you had access to a quantum computer. But the classical optimization part, which is at the heart of all these algorithms, is something which you can run now without setting up the parameter shift rule, which we had in project number one, running these experiments many, many times and measuring on all the qubits, as we did in project one. So we leave it a little bit to you guys to actually choose which approach you want to use, and you will not be penalized in project two for that. But in project one, we were explicitly asking for you running a series of experiments as you would do on a quantum computer. So I hope that is pretty clear. We are going to repeat some of these arguments when we also discuss the projects. So you should feel free to use the standard optimization algorithms, like if you're implementing neural networks, you could use Adam, as long as you have the gradient, or you could use any of the scientific Python encoded libraries for optimization based on quasi-Newton methods, like Broyden's method, Broyden et al., etc., etc. Any questions so far to this? Okay, so let me quickly remind you of some of the things which we discussed, which we had for last time. So this is a optimization problem, the QAOA, and it's given by a binary optimization problem. So that means that the values which we're looking at are zeros and ones, and it's normally an NP-hard problem. There is no known polynomial time algorithm, and the approximation is actually to approximate to find some x which achieves alpha being less than equal than 1. The nice thing with this optimization problem, so this is a quadratic optimization problem. And this is a problem which many of you have encountered before. So let me just quickly remind you a little bit of this type of problem by just switching over to the whiteboard. So let me just do that. So in standard machine learning or in standard optimization, what you often have met is something like a function which is given by f of x. And in many cases, this function is the result of a Taylor approximation around a specific value where we keep terms up to the second derivative. And when we keep terms up to the second derivative, we would then typically have, based on a Taylor expansion, we have some x0 here. Then we have some gradient term. So I'm just going to write this now as a vector, which I call for x here. And this is actually normally x minus x0 transpose. and it's multiplied with the gradient of f of x evaluated at x is 0. So I'm just writing it like that. That's the gradient. That's the term to first order. But then we have the second order term. So this is based on a Taylor expansion around a point. And then we have the second derivative, which we normally call for the Hessian matrix. So I'm just going to write this second derivative as an h. And this is obviously also evaluated at x equal to x is 0. And it's then multiplied with x minus x0. So if you think of a Taylor expansion, if these are scalars, we don't need to worry about matrices and vectors. But if it's more than one variable we're dealing with, then Taylor expanding the function f of x around the point x of 0 leads to an approximation where we have the first derivative and the second derivative. Now, this is the basis for the type of functions which we are looking after. And then what we want in the optimization problem is actually to drive the gradient of f of x to 0. So if you look at this function here, you could actually now, if you replace this one, and let's just call this for a vector beta. So what we would have then would be that this f of x is then equal to some f of x0 plus beta transposed times the gradient, and I'm just a little bit sloppy with notation here, plus beta transposed multiplied with a half, and then we have the Hessian and beta here. So this is the more compact expression. And you see now that this is normally what we would call a quadratic function in the variable beta. And then we're going to take the derivative of this f of x. And when we take the derivative of f of x, we end up with a problem which is a standard linear algebra problem, which many of you have seen. So if I take the derivative of f of x, and I want to drive this to 0, so just keep that f of x 0. So this is us Taylor expanding around that point. That means simply then that we have a function where we now have the, if we take the derivative with respect to these variables x, then we get a function derivative of f of x, which we hopefully know. And then we have a matrix x, h, multiplied with a vector x. So that gives us a problem which goes like beta is equal to some del f of x here. Roughly, that's the problem. So we can replace that one with just a known function g of x. So we are assuming that we can calculate this function. And then we have the unknown quantity here, beta. So this is the typical linear algebra problem which we end up with. And probably you have seen this in many, many disguises. If you took a course on machine learning, essentially what you do then, and which also leads to Newton's method, is actually a Taylor expansion where you stop at the second derivative. And so the QAOA problem, which we had last week in the slides, is something which is a lookalike of this quadratic problem, except that the values x take only binary values. So let me just go back. So this was a kind of putting things in a broader context where you have a quadratic function, and then you want to optimize that one, and that leads to a standard linear algebra problem. Okay, so let's go back to the slides. This is a pretty well-established problem in optimization theory. And let me find the slide. Let me just stop just a moment here. And let me find back the slides from last week. So I wanted quickly to remind you of some of the basic elements before we just move on to neural networks. So essentially what we have, and where we've taken away the linear term in x, is a problem like this. This is a typical quadratic problem. And you can then expand this in terms of some coefficients, and then you have xi, xj. This is typically the way you would have it. And we're also assuming, in many cases, this matrix Q is actually symmetric. If you look at the second derivative of the function you're going to optimize, this function is normally a symmetric function. So x of I takes only binary value. So it's a quadratic unconstrained binary optimization problem. And there are quite many types of these problems. The nice thing is that x of I squared is equal to x of I for binary variables. And all diagonal and off-diagonal terms then contribute. And any polynomial objective of binary variables can be reduced to this kind of a QAOA, so a quadratic unconstrained binary optimization problem by degree reduction. So in general, this is considered as an NP-hard problem. The thing which is nice with many of these things, and that's why when this algorithm was developed, is that you can actually rewrite this type of quadratic optimization problem in terms of an Ising model-like problem. And the Ising substitution, you could then think of, instead of having 0 and 1s, it's a binary problem, you just have -1 and +1. And then there is a simple transformation where the x of I then relates to the spin. And then you can rewrite that function you want to optimize in terms of a Ising model lookalike. And the Ising model is very nice because the matrices S can immediately be translated into Pauli matrices. And when we have something which is translated into Pauli matrices, this is ready for a variational quantum algorithm, which actually is the QAOA is an example of a variational quantum algorithm. So any QAOA problem is actually equivalent to an Ising model where you have a problem with a Hamiltonian, which is a function of the spins, and you would have a linear term, and then you have the additional term here. So this is just a simple rewrite. So if you then think of the Ising model, this is one of the reasons why the QAOA algorithm is such a popular algorithm, is that we can actually rewrite the Ising model in terms of Pauli Z matrices, as we did in the VQE algorithm, except for the VQE case which we looked at, we had also Pauli X and Pauli Y matrices. So if we do that with our standard computational basis, then we know that the Hamiltonian which we have, which is in this problem, is called the cost Hamiltonian. So this is the function we want to optimize. Okay? And that gives us a function which is the what we might call the quantum version of the Ising model. And it's actually, and it's diagonal in the computational basis. And you can see that if you act on any of these states here, where Z of I is 0 and 1 here, you can see that this is actually a system which has these states as an eigenbasis. So that means that the function we want to optimize is the C of Z. So the ground state of HC actually encodes the optimal solution. That's the basic with the problem which the algorithm, QAOA algorithm. So we do a QAOA to Ising. So we have a coefficient mapping. We have the Ising coefficients where we typically have a parameter Jij. We have this formula here, which we can rewrite like this. And then we have the transformation of the Xi to the Xj's. So we get these linear terms, and then we just have a constant which is absorbed into the energy offset. So minimizing this function here over this set of variables is identical to finding the ground state of this Hamiltonian, this Ising Hamiltonian, which is just shifted by a constant. So we have something which is ready for translating into quantum gates. And in the slides here, you can see if I take an example with n equal 2, then this matrix Q is equal to, it's actually not so difficult to see that. And then you end up with a problem like this, where the CQ here is actually given simply by this term with x1 and x1 times x2. And if you look at the Ising coefficients, then you can actually read off, the different parts of the Hamiltonian here quite easily. And you see exactly what kind of function you're going to optimize.
CQ is where?
Yeah. Now, so this is just a quick reminder of this type of setups. And then there is another problem, which is called the max cut problem. So which simply says, given an undirected weighted graph, with a given number of vertices and edge weights. But then you want to find a partition that maximizes the total weight of cut edges. And binary variables, this is a classical max cut problem, which is also implemented in the program examples which you have in a Jupyter notebook. So as I said in the beginning of the lecture here, I haven't finalized yet the recording from last week, but hopefully the slides here contain enough information that if you can actually use them if you want to implement the QAOA algorithm, in particular if you're also interested in applications to finance. So the max cut problem is something you can easily derive because you get a function here where you have taken the standard Ising model, which you rewrite in matrix form, and you have a cubo matrix like this. And then the problem you want to optimize is this one. And more compactly, you will see that this is a valid cubo term. And then it's conventional to write this function you want to optimize. This is now the cost function or loss function you want to optimize in terms of these weights, which relate to the edges, and then multiplied with the values of x times xi times xj. And what I've done here in the slides is to go through the detailed calculations where we look at the max cut problem and make a transformation from cubo to the Ising model, and then translate everything in terms of Pauli operators. So the problem, the max cut problem is something which is rephrased like this. And then you promote to operators. So you want to implement this on a quantum computer, which means that we want to translate this into specific gates. And then what you will find then is that when you do that, it corresponds when the optimization problem, optimizing this one, means the same as minimizing the minus h, which is then the same as finding the ground state of this problem. So there's an example in the slides where I actually look at the max cut problem for a graph with 4 nodes. And then you can actually see that there is an optimal cut with 1, 3, and 2 and 4. And these are the bit strings which you get then when you're setting it up. And if you look at h acting on this bit string, then you should actually get, when you act with this operator here, this is your Hamiltonian, translated into Pauli gates, this is actually what you should get. And then the thing which we implement then is actually to implement this in terms of a variational problem. Because if we do the minimization, we know that when we now have rewritten our cost function, we know that this actually satisfies a variational bound. So you see immediately now that since we have translated this cubo problem into so we have a quadratic problem, and we have been able to rephrase this function we want to optimize in terms of an Ising model type of problem, which we then can rewrite in terms of Pauli gates. Then we know that this has to satisfy when we have a trial state, which in our case could be the ground state of the system. That's the one we are targeting. Then we want to optimize this expectation value, and max cut is a maximization problem. If we do the minimization, then if we have minus HC, it becomes a minimization problem. So the whole thing now is restrict to a parameterized family of wave functions, and you optimize over theta classically. So if you think back what you did in project 1 with the VQE, this is actually a lookalike of the VQE, except that now you have a Ising model like Hamiltonian. It's pretty neat, actually. I think it's a very cute algorithm, and it's something which then can be run on existing quantum computers where you have lots of noise. And this is essentially the optimization problem. And if you put a minus sign, you get a minimization problem. And this is essentially what we did with the VQE. Because just to remind you, when you had the variational quantum eigensolver, you prepare the state, And the way you would prepare the state, and if you go back now to project one, because what we are doing here, there's a reason why I'm repeating many of these things. And that's because if we look at quantum neural networks, they are also given in terms of what we call parameterized quantum circuits. And if we rephrase them as a variational an optimization problem, where we put a minus sign in front of the Hamiltonian, which we have defined, then everything can be looked at as a variational optimization problem. So when we did project one, what we had then was to prepare the state on a given quantum device. And these rotations which we had included the Hadamard operations, rotations on a single qubit, but we would also entangle the qubits, because if we didn't entangle, we would just have a product of states. And then if we had just product states, we would get a final state in case we have a correlation in the data among the states. Then we would get something which was away from the exact ground state. So some of you actually in project one, you did that. And you show that if you just have a product state, you would never get the exact ground state of the system, which is a correlated one. So this operation one includes also us having gates, 2 qubit gates, which entangle the qubits. And you can actually make these circuits as deep as you want, but the deeper you make them, the more parameters you have to optimize. Then what we did was to decompose, and in our case, we have this Hamiltonian HC, which is the Ising model lookalike. We decompose it into polystrings, and then we measure the expectation values. So in the code examples, as I said, in the codes, when I'm doing the optimization, I'm not running with a number of shots. So that's something which I left out. I'm just using a classical optimization algorithm here. So I'm not simulating as if I was running something which is close to what you would do on a quantum computer. Then we found in step 4, when we have evaluated these expectation values, we go back and get the expectation value of the energy for the specific angles, and then we update theta with the parameter shift rule, if we can do that, depending on the angles. And then we go back to step 1 and keep repeating. So the QAOA is actually a VQE with a problem-specific ansatz, which is determined by this HC and this HM, which is coming, rather than an ad hoc parameterized circuit. So there's something which then also brings in here additional features, and that is why we also need to use trotterization, which some of you have actually encountered when you took a course on many-body physics. So this H of M is normally called the mixer. It does not commute with HC, which is diagonal in the Z basis. So it generates non-trivial transitions, and its ground state is actually a linear superposition of zeros and ones qubits. And then we have a unitary, which now contains the Z of M, which is then simply the tensor product of all these rotations which we can do, of single qubit rotations. And that's pretty easy to implement. So the QAOA, the trial wave function, or the circuit which we end up with, is something which then contains this additional part, and then it contains the HC part. And the variational objective is actually to optimize this problem here. So the initial state is often a uniform superposition here, where these H's are actually Hadamards, which you act on every qubit. So that's a pretty common way to initialize the system. And there are 2 representations. One represents complete ignorance about the solution. All 2 end candidates have equal amplitude. If you look at the physical interpretation, the ground state of this mixer state is actually, which is given by this one. So it's actually, this state here can be seen as a ground state of that state. So the system starts in the ground state of the driver and then gets adiabatically guided towards the ground state of HC. So the preparation cost is actually the number of Hadamard gates. And then you have the explicit action. So I'm not going to repeat all these technical details, but I wanted to say a little bit about the link with, there are several examples here, but I wanted to say a little bit about the link with quantum neural networks. So these are just technicalities about the method. So we can actually view this QAOA algorithm as a quantum machine learning model. So what it does, it trains parameterized quantum circuits by minimizing a loss function. And this is essentially what we end up doing when we deal with quantum machine learning methods like quantum neural networks or quantum Boltzmann machines. So it means that you can think of this as a kind of structured quantum machine learning method. So the architecture is fixed by the cost Hamiltonian and this mixer, which is not chosen freely. So you can think of that as a model which is much more structured compared to what you're going to see now with the quantum neural networks. Because we have an optimization problem, which is a binary problem, the QAOA, which then leads to a specific H of C, which is an Ising model lookalike, which is well defined in terms of Pauli Z matrices. And then we have this mixer, which is the way we prepare the initial state. And then the observable is actually the expectation value of this H of C. And the parameter space is normally pretty small and very well structured. So a general quantum machine learning model, on the other hand, can actually be viewed as this QAOA with a data-dependent cost Hamilton. Because in our case now, we are not looking at the specific way we are encoding the data. We are coming back to this now. Okay, so this is just a kind of preparation to what is going to come. There's also discussion of how we encode the data, etc. So this is something which is for the material last week, but I wanted to bring this up because there are many parallels between what we had in the slides last week and what we are going to look at with quantum machine learning. So let's switch back to the slides for this week. So let's just stop that one, and then we So I'm exposing you to more slides this time because I want to have you with me on the more overarching picture. So let's just put in a full screen mode here. So if we now look at quantum machine learning, so we've had a taste of it when we look at the QAOA algorithm. So it integrates quantum computing with machine learning to exploit quantum advantages. So we have quantum parallelism, quantum entanglement, which becomes important. And actually, when you're setting up a circuit for a quantum neural network, you can try to set it up without 2 qubit gates, which entangle 2 qubits. And then you will see that if you just stay with a product state, you will have much less expressivity. So you're not using quantum entanglement. And this is actually a very nice thing to do. So if you set up a quantum neural network with just 2 qubits, for instance, then with that, you can actually look at what happens if you don't entangle the qubits. So that's a simple case, which you can actually follow almost by hand. So if we now look at these noisy intermediate phase quantum computers, clearly we have this NISQ, which you probably have seen many times, noise intermediate state, intermediate scale quantum devices. So we have a long decoherence, we have decoherence limits, which limits the depth of the circuit. So it means that we cannot make it long enough. So actual calculations now, where people have implemented quantum machine learning methods like quantum neural networks, are nowadays limited to something like 10 to 12 logical qubits. And this is a case which is normally what we normally would call a simpler. If we translate this into classical neural networks, it often leads to what we would call a small problem, or even below intermediate size type of problem. So the core questions, which is much debated, is actually when does quantum hardware give a genuine advantage over the best classical algorithms? That's a topic which is debated again and again. So if we now think of a quantum neural network, the way we are going to do that is that we are going to have a variational ansatz, which now contains trainable parameters. And then there is a part here where we translate. So this is a topic which we will say a little bit more about next week, actually how we translate classical data. So you can think of quantum machine learning as a set of algorithms which can act on quantum data. But if you think of, for those of you familiar with machine learning, if you're looking at, let's say, the MNIST data set, this is a data set which contains images of handwritten numbers from 0 to 9. So then you would typically encode every such number into a bit pattern. That's the standard way which is done classically. So quantum mechanically then, if we are dealing with a quantum computer, we would have to have an intermediate step, a beginning step, where we encode the data, the classical data, into quantum data. So this is something which can actually limit a lot of the calculations. And then we have a variational ansatz, where we have the training parameters, and this is as before. And then we have the type of output which we are interested in. So training the QNN means actually finding parameter data that minimizes a classical loss computed from repeated quantum measurements. So if you look at the pattern here, the biggest difference between what you had before when we implemented the VQE is actually this part here, where we are encoding the data in one way or the other. So I will say a little bit more about that next week. Any questions? So typically, if you now think of a 2-qubit circuit, so there is going to be a part U of X, which would take the initial data. So you could think of that given in terms of a rotation matrix, which encodes data as rotation angles. And we're going to look at the explicit examples of that. And then we can have a rotation around the y-axis. Keep in mind, again, as you did with the VQE, you can make these circuits deeper and deeper. The deeper you make them, the more parameters you have to train. So this part which you see here is actually the one where you encode the classical data into quantum data. Then you have the rotations. You can have some C-naught entangler. And then you have further rotations. So you have actually 1, 2, 3, 4 parameters. And then you have an output, which then could be an expectation of the poly-Z matrix acting on the first qubit times this one. This is not so different from what you did with the VQE. So I hope you don't get offended if I keep repeating this link with the VQE. But the whole thing with translating and setting up a quantum neural network is actually to simply reuse what we have seen before, except that the delicate thing now is how do we encode the quantum data or the classical data into a quantum computer. So if you look at a feature map like this one, so this would be the typical Hamiltonian, which we have. And this could be some kind of mapping in terms of poly-Z gates. So we would then have a rotation here. Then we have a new rotation, and then we could actually have the data, which is a coupling constant of a spin Hamiltonian. We have a circuit, which then is the quantum time evolution of the system. And we have some pairwise terms which create entanglement between these typical features here. So this could just be an example of a feature map as a Hamiltonian evolution. So the variational unitary, which we have seen before, is typically generated by a Pauli Hamiltonian of this type here, and where this H of theta then contains parameters, and then we have the Pauli matrices. And where the P alphas are the different matrices which we have seen again and again. And this is just a tensor product of the different combinations of Pauli matrices, as we had before. And then we have the Baker-Campbell-Hausdorff expansions, means that since these components here may not all commute, so that means that we may get some nested commutators. So each commutator level adds higher body correlations. And this is, for those of you familiar with copper cluster theory, this is actually a lookalike of that. So some of you have taken a course in many body physics, and I'm bringing in many of these connections because then you see the links between things you have seen before. Not everybody's familiar with that. So you could have a implementation of this where you have the different rotations, you have an entangler, and then you have new rotations, etc. So the typical, if you set up the full diagram, it could look something like this. So you could have the feature which is encoded here. That encodes the data. This is for 4 qubits. And then you have 2 repeated variational layers. So we have 4 parameters here, and you have 4 new parameters. You have an entangling C0 gate, for instance, which entangles the qubits. You can also entangle all of them. So this is just an example of how you could entangle. And then at the end, you make a final measurement. So this would be a typical example of a quantum neural network when you have more than just 2 qubits. Now, when we calculate the gradients, again, since many of the gates will actually be written in terms of this combination of Pauli matrices, keep P is just a Pauli matrix, and then the gradient can actually be calculated exactly. So keep in mind that this applies only if this is a clear term expressed in terms of Pauli matrices. So this typically requires only 2 circuit evaluations per parameter, as you did with the VQE. There is no finite different approximation. Obviously, if you cannot implement this one, then you would have to add some kind of finite difference approximation. And there is typically no additional qubits needed, like when we discussed the HHL algorithm or the QPE algorithm, we had additional registers. So we had the control register, and then we had the system register. So remember that the QPE, for instance, and also the HHL algorithm we discussed, are algorithms which often give very lengthy circuits. And then we can calculate the gradients from this commutator, which we have here. And the gradients are quantum response functions. That's the way we would typically interpret them. I may skip actually this one and come back to that one next week. I'm going to give you, what I want to do now is more to give you the general overview. And next week, we will say a little bit more about the quantum Fisher information. And this is a typical metric, which is actually used on this manifold of variational states. And this typically measures the distinguishability of nearby quantum states. And the practical formula, which is often used when we calculate this quantum Fisher information, is actually to employ this formula, which you see here. And that gives us a natural gradient when we now look at the calculation and update of parameters here. So for those of you who are familiar with variational Monte Carlo calculation, this is something which is called actually stochastic reconfiguration. So if these are details which we don't need to think so much of presently. And then after that, when we look at this typical quantum Fisher information, there are specific ways of encoding it. And I'm going to say something about that after the break. And after the break, we're also going to look at the links with the other methods and also how we can encode the neural networks and also say something about basic neural networks, the classical ones. Okay, I see we are a little bit over time, so I thought we could take a small break and just stretch legs a little bit. So these are some technicalities about the way we evaluate the gradients. And you don't need to look at this now, also because some of the things are a little bit more technical, and in classical Monte Carlo calculations where you evaluate let's say the energy of a given system, there's a method which is called stochastic reconfiguration, and that uses what's called the classical Fisher information, which is a way to approximate the second derivative. So for those of you who remember from optimization problems, we have in Newton's method, when we apply that one, we have something which is in the update. We have the gradient of the function we want to optimize. And then we have a matrix, which is called the Hessian matrix, which we calculate the inverse of. Normally, we don't evaluate that. We typically replace this F with a learning rate. So in case you want to evaluate the quantum Fisher information, which is actually an approximation to the Hessian matrix, which contains the second derivatives. If you don't want to do this, which involves stochastic reconfigurations, etc., you can replace this F inverse with a parameter, which we just call the learning rate. Like we did in project 1, when we looked at the gradient optimization in the classical part. So we could use different ways of setting up this second derivative here. So the practical formula, which then approximates the classical Fisher information, is actually called the quantum Fisher information. But that's a technicality here. And in the next slide, I also included some additional technicalities on how you would actually calculate that one. And this is something which you can calculate with a Hadamard test circuit. And for the off-diagonal elements, you would typically use 2 Hadamard tests with pi plus minus pj. So you don't need actually to include this. So I'm just adding it in case you want to have an optimization part where you have elements of the Hessian matrix. So this is just something which perhaps is, I mean, for those of you who have taken a course in machine learning, you know that this optimization problem where we have the gradient times the inverse of the matrix, which contains the second derivatives of all the parameters of the cost function with respect to the parameters. This is a quantity which you can evaluate with a technique called stochastic reconfiguration, but you can also replace that one with just a parameter learning rate and then just rerun the calculations. So these are some technicalities which you can implement or not. And then typically when you have this time-dependent variational principle that projects the Schrödinger equation onto the tangent space of the variational manifold, which you're optimizing. And that means that you would also have this Fisher information if you want to use that. You don't need to do this. You can actually just replace F here, F inverse with a parameter, and then just rerun with different learning rates. So this is just a way to actually mimic something which actually looks like what you have in classical optimization problem with quantum mechanical systems, where you can use a method which is called stochastic reconfiguration. So if you're not familiar with that, some of you may have taken a course in many-body physics on Monte Carlo methods, and then you have encountered the stochastic reconfiguration. So one of the problems is that the variance of the gradients, the gradient variance normally scales exponentially with the number of qubits. And random deep circuits from approximate unitary designs, the output distribution concentrates something near what's called the harm measure, and local observables concentrate around their mean, making gradients to vanish. And this is actually a problem with the training of quantum neural networks. So this is an ongoing research problem about barren plateaus. For those of you who took a course in machine learning, you may have encountered the topic of vanishing gradients or exploding gradients. This is something which is not so far away from that. So the variational quantum circuit, if we now look at what we are doing with a quantum neural network, is that we have a piece here which encodes the classical, if we are looking at classical data. So when we would then have a part which encodes the data into quantum data. And then we have different parameters which are then making up the variational circuit. And then we have different C0 gates which entangle. And then finally, we do a measurement. I'm going to skip some of this. There is a discussion of some of the codes, which I will come back to. But I wanted to say a little bit about the type of connections which we have between a quantum neural network and methods like a variational quantum eigensolver, which we mentioned partly before the break. So we would have the variational principle. We optimize the Hamiltonian with respect to a set of variational parameters, where the ansatz is a set of unitary operations plus controlled operations which entangle the qubits. And then the measurements, when we have decomposed the Hamiltonian in terms of polygates, is then simply given by a measurement with respect to these expectation values. And then each of these is measured on the quantum device. And then we have the parameter shift rule. So this is essentially the VQE. And if you think back at, for those of you who took a course in many-body physics, if you think about the copper cluster theory, this is actually a kind of lookalike to copper cluster theory, what you're doing here, especially for the unitary copper cluster theory. If we look at the QAOA, which we had from last week, so this is just linking the quantum neural networks with what we have seen. Then we want to maximize a classical cost function over these bit strings. And we encode the Hamiltonian, which is an Ising model lookalike. And then the ansatz, which then reflects the depth of the circuit, is then given by this mixer Hamiltonian, which then essentially contains a set of Hadamard operations, which is this part here. And then we have the different rotation gates. And with that, we have, when we've done that, we need to use, since these operators, H of M and H of C don't commute, then we need to use a trotterization with adiabatic evolution. So the max cut, if we then look at this HC, we would then have a set of Hadamards. We entangle, we have a rotation gates with the parameters, and we can entangle again, and then we can make this deeper and deeper. And at the end, when we look at the trotter approximation, we are essentially evaluating this unitary transformation here. And if we relate this to quantum neural networks, we have to evaluate the gradients, which are normally calculated either by the if you're looking at the QAOA, we often end up evaluating the gradient by finite differences because the parameter shift cannot be used because HC has a multi-valued spectrum. If you're using with just the Pauli Z gates, this is actually much better, much easier. But in general, for the QAOA, you would actually use finite differences. And there's no guarantee that the function is convex, but it has structured correlations. So normally we would see the QAOA algorithm as a subset of the QNN, as I said, where a QAO, the quantum approximation optimization algorithm, is a quantum neural network with specific Hamiltonians instead of a general hardware efficient ansatz. That's the one of the ways you can actually look at that. So if you look at it, if you think of the ansatz, the QAOA, which we discussed, which we had last week, we have a fixed Hamiltonian. We use a adiabatic evolution, and then we have a typical optimization parameter. The VQE is general, it's variational, and then we are just targeting the ground state, and it has many parameters. There's one thing which, as I said in the beginning, I was a little bit unsure whether I should talk about support vector machines, because that would easily have taken a full lecture for just the classical support vector machines. But the support vector machines and the quantum support vector machines are based on something which are called kernel methods. Now, the classical support vector machine involves a set of parameters alpha which are being optimized, and where you then can have a function k which can be which is normally a way to transform the data, or it could just be the raw values of x. So y is your target value. This could be a binary output, 0 and 1, true, false. And the kij is actually the input data, the x's. And this type of kernel is something which in quantum mechanics is actually replaced with a wave function. And that's the link between standard support vector machines with a kernel which may not be equal to just xi and xj, but it could represent a transformation of xi and xj. This is often done as a trick in support vector machines in the optimization problem. And then you would have a Lagrangian type of function which you would optimize. And this is the one you would solve, how to say, classically. But in this case, you would actually replace this kernel with a transformation where you take the ansatz for the wave function, which is now given by a quantum circuit. And in that specific case, you can then see a set of Hadamard operations, and then you can have C0 gates, so you can have other gates which entangle the system. If we look at the HHL, which is also a type of problem which could be thought of as almost a kind of a parameterized circuit, not exactly. For the HHL, we ended up solving this problem here, where X now is a quantum vector. And we have a spectral decomposition, which was given by this expression, which you see here. And the HHL implements the inverse eigenvalues via the quantum phase estimation. So you have the quantum phase, which encode eigenvalues in a register. You have a controlled rotation, and then you uncompute the QPE and post-select the ancilla with the qubit 1. And that means that basically the circuit is actually a QPE, the inverse ones, and then you uncompute the QPE, and then you act on a linear combination of the ancilla qubit, which is this one, which is a linear combination of 0 and 1, and you project out the 1. So if we look at the kind of three fundamental structures of quantum machine learning methods, the way, if you now want to compare what we have done in the last 3 weeks, the typical approach then, if you look at a quantum machine learning method, in particular, if you look at the quantum neural networks and also the VQE and the QAOA, this is normally a variational evolution. And if we think of the other method which we have looked at, the HHL and the quantum phase information, the quantum phase estimation, this is actually something which is going through inverse quantum Fourier transforms. We would normally call this methods based on inverse mappings. So the HHL gives us an exact inverse operator. And this is one of the reasons why it has been very popular. Oops. So let me just take away that one. And then for the quantum neural networks, the VQE and the QAOA, this is some variational dynamics where we have a set of parameters which we are then optimizing. So we end up with what's called a variational a variational quantum circuit. So all the methods, if we want to put this together in a more general way, is that all the methods, they are based on the spectral decomposition of a given operator. So the HHL transforms to the inverse. The QNN and also the VQE, which we had in project 1. Oops, I have to stop that one. Oops. Let me just a moment. So the QNN, a quantum neural network, and the VQE as well, they actually learn the eigenstructure via gradient descent on a variational manifold. So typically what you have is an exact in the HHL. You actually calculate the exact inverse operation here. And in the standard quantum neural network and also quantum Boltzmann machines, which we will discuss, and quantum pins, this is something which is actually a variational approach to the problem. So advantages and future directions which the fields are going into. So the HHL and the QPE, it actually depends a lot on the decoherence and coherence properties of a quantum mechanical state. When we look at this noise intermediate state quantum computers, the VQE, these are variational quantum approximations. Both the VQE and the QAOA and quantum neural networks, they actually have an unclear general advantage. So there's a lot of debate now of which is the best method. If we have a fault-tolerant quantum computer, then clearly the HHL and the QPE will typically be preferred methods. But since we have noisy quantum computers with errors and et cetera, the type of algorithms which we end up using are those which we have discussed both in project 1 and also now with the QAOA and also with quantum neural networks, which we are going to dive a little bit more into towards the end of the lecture here and also next week. So what I wanted to do now is to bring up the possible implementations. But before we do that, I wanted to remind you quickly of classical neural networks. So if you think of a classical neural network, as a quick reminder, what we typically have then is a so-called input layer. So the data are classical data. And then we could have a set of nodes which represents the data. So we would typically call this x0. We have a node x1, etc., down to some xn minus 1. And the encoding is often pretty straightforward. So if you have images with a given number of pixels, so suppose you have 8 times 8 pixels, which means that you would need 64 input nodes for every image which you want to recognize or make a prediction of, then you would typically translate this input information in terms of a bit representation, classical bit representation. And then this is then fed into the so-called hidden layers. And you can have an architecture with many hidden layers. So you can have one hidden layer here, and you can have further hidden layers, and they don't need to be of the same size, as many of you are pretty familiar with. And this moves on. So these x's here feed into the first hidden layer, etc., etc. And then we can feed in the same information to the next hidden layer. And this just continues till we get to the output layer. And the output layer is problem specific. So if we're just interested in a function value, this would just output one function. So we can have a given set of nodes here, and that receives information from all the hidden layers. And each hidden layer has a set of activation functions and a given set of nodes. And the training parameters are the weights and the biases of the network. Then this is fed into a cost function, which we typically label as a function C of theta, which then depends on the parameters. And this receives as input some variables y. So it produces a y tilde. And the cost function is the one which then is optimized and compares the y tilde, what the model produces. So the model is now given by the architecture of the neural network, and the output and how it links with the data we want to reproduce, these y's, depends very much on the type of problem we have. So if you think of this MNIST data set with 10 handwritten numbers from 0 to 9, then you would have 10 classes and then 10 outputs. And whether you have a likelihood for finding number 0, 1, 2, up to 9. And then you would train on a given set of images. So you could have something like 10,000 images with a given set of pixels. This MNIST data set has, the main data set has something like 60,000 images, with each image being represented by 28 times 28 pixels, which means that you have something like a 700 input nodes for every image. And then you train a model where these parameters, theta, are the final weights and biases, which you then use to make a prediction. So when you have trained the model, which means that the gradient of the cost function here is driven to 0, or as close to 0 as you want or can, in principle. This depends on the CPU cycles you have at your disposal. Then at the end, you have a parameter which has been trained where you have found the optimal parameters theta hat. And these are then used by you to make predictions. So then you could use this to generate new images, or to have, if you have a generative method, or you could simply discriminate between number 0, number 1, etc., when you feed in an image which was not included in the training. So this means that when you now look at a quantum neural network, on the other hand, we are going to train a set of parameters, but in our case now we would have the input here, which can be quantum data or classical data. So we just label this as an input layer. Then this is transformed by a set of typically Hadamard rotations, and we just call this a U of X. So this doesn't have parameters. So we actually encoding the data into quantum data. So quantum, I just call this for quantum translation. And next week, we are going to look at examples of how we do that. And then the input can be classical, quantum. If you think of the MNIST data, then the MNIST data is a data set which has just classical inputs, just the pixels of images. So in that specific case, we would have to translate these set of pixels into some quantum state representation. Then the next part, which we have, is the one which represents the parameterized quantum part. So we would call this for a parameterized quantum part. And this is the one which then depends on the different angles, theta. And then finally, so this would also contain C0 gates, etc., etc. So we entangle the different qubits. And then at the end, we have the measurement. So this is roughly the structure of a quantum circuit when we now are developing a quantum parameterized circuit, which is going to be the equivalent of a typical classical neural network. So let's go back to the Jupyter notebooks and stay a little bit with them for the rest of the lecture. And so let me just bring that up. I just need to find my let me see, I should have it. Let me just see again why I don't get this slide up. There we are. Sorry, I didn't see the window here properly. So if we just scroll down a little bit, because you will find a little bit a repeat of the machinery which we found. So as I said, when we are setting up a variational quantum circuit, there's going to be one part, which is a unitary, which can be composed of rotations. That depends on the input data. And then you have the variational circuit, which is this W, which is often built as a product layers of different quantum rotations and C0 gates, etc. And the output is normally a scalar or vector output, and where we measure one or more observables on the final state. So the typical output then of this kind of variational quantum circuit is then given by this expectation value here. And where the state here is now given by the way we encode the information and the variational parameters which we're going to optimize. So that means that if we are looking at a specific observable B of k, which could be just one of the Pauli gates, then this is the quantity which we would have to evaluate. And commonly this B is a Pauli operator. So in practice, one runs many shots on quantum hardware or simulates these circuits classically. So I just wanted to emphasize a little bit this line here, because in the project 2, you can decide whether you want to simulate it classically, which means that you then don't need to think of running number of shots like you had to in project 1. Or alternatively, you can actually simulate this one on a classical computer. So that means that you set up the gradients, you run the calculations without thinking of this as a numerical experiment where you repeat the shots again and again. Okay? So it's a short summary. A variational quantum model maps inputs to outputs via the hybrid quantum classical procedure. And during training, the classical optimizer adjusts these variables theta by gradient descent, and to minimize a cost function like the mean squared error, which is defined in a data set. And because the mapping is inherently quantum, these models can in principle harness the high-dimensional Hilbert spaces for richer representations. However, unlike classical deep nets, these variational quantum circuits may face unique challenges such as gradient vanishing, which we actually discussed a little bit later. So if we now look a little bit at the way we can do the encoding, so what you will find here is basically what you will see in the slides as well. So quantum neural networks are essentially multi-layer variational quantum circuits that mimic classical neural networks. You can think of each layer as adding a non-linear quantum neuron to the network. So this is a kind of equivalent. So I'm going to read what you have here so that you can see the link between a classical neural network and a quantum neural network. So if you think of the layer which you have in classically, you can think of each layer as adding a non-linear quantum neuron to the network. A simple QNN is a sequence of encoding and variational layers. So more structured architectures, you can also find that, like quantum convolutional neural networks and quantum long short-term memory networks. So in a quantum convolutional neural networks, qubits are entangled in a localized pattern to mimic convolution and pooling. So we will essentially stay, and with the example next week, we are simply going to stay with a quantum neural network and an application of that to the solution of differential equations. So a crucial aspect are the following, is actually that is how classical data are embedded into a quantum state. And next week, we will actually look at some of these details on how we can actually encode the classical data. So you need a basic encoding, so you can map each bit of X or feature to a qubit state. So that's a very typical case. And that quickly tells you, if you want to use this recipe, if you say, suppose you're looking at the MNIST data, where you have a bit encoding of an image, you see quickly that you will actually need quite many qubits to encode that information classically. So as I said, today I just wanted to give you the broader picture. And next week, we are going to look at, in particular, at the input encoding. So there is another type of encoding, which we will also discuss next week, which is called angle encoding. And that uses rotation gates to encode real values on qubit I. There is something which is called amplitude encoding, where you would actually embed X into the amplitudes of a multi-qubit state. This actually requires complex circuits to prepare. The simplest one is normally one, the basis encoding, which we will detail a little bit more next week. So the choice of feature map actually affects performance, and no single encoding is best for all tasks. So keep in mind that when you look at a quantum neural network, perhaps one of the more difficult parts is the encoding of the data. So when you've done that, then you can think of a general QNN as a parameterized unitary acting on n qubits, followed by measurements. So there's a figure 2 actually, which I don't have here, but which you see in the PDF file. You will find in the PDF file a generic QNN with several layers of trainable gates. And each layer can entangle qubits, building up complexity. So when you are running your first quantum neural network, you could do as you did in the VQE. Some of you actually did these tests in project 1, where you actually run the calculations without any 2-qubit gates, which entangles the qubits. So then if you do that, you would see that you have less complexity because you're not entangling the qubits. And you will get results which you may not be satisfied with. So in general, what you can think of is that the type of trainable layers, each layer entangle qubits, and you perform the rotations, and then you build up complexity. And the output is normally a classical vector of measured values, which is pretty common to what you have in a classical neural network. So the simple feed-forward QNN structure contains then these 3 steps. So you embed, convert X to quantum states via this operation, U of X. Then you have the variation layers, and then you repeat L blocks of parameterized gates. And each block may act on all or just a subset of the qubits. So keep in mind that as you saw from some of the figures in the PDF file, we can actually have repeated blocks of parameterized gates. And that can involve rotations with angle dependencies, a set of CNOT gates, etc., etc. And as I said here, each block may act on all or just a subset of the qubits. So clearly, the more qubits you act on, the more complex the circuit and the more lengthy the operation. This is also one of the reasons why the quantum neural networks, the applications nowadays, are actually just limited to few qubits, which means that the typical cases which have been studied in the literature are often toy model cases. So if you think of the MNIST data, what has often happened is that you run calculation with just 2 of the numbers. because the dimensionality quickly explodes. And you will need quite many qubits in order to run a serious comparison with existing machine learning methods. So presently, quantum machine learning cannot compete, except for some simple toy data and some low dimensional problems with standard machine learning methods. And that's simply because, as you can see here, each block, which then represents, in a way, a hidden layer. So the hidden layers are now replaced by all these unitary transformations. And these contain the angles which you want to optimize. Does that sound? This is a parallel with a standard neural network. And then you have a measurement where you measure selected qubits or observables to obtain the output predictions. And then you feed back. So this is the feed-forward structure. So if you think of, for example, a simple two-layer quantum neural network on 2 qubits, then you might actually apply first the encoding. This is the one which acts on qubit 1, x1, and x2. So you encode classical data into quantum data. And we are going to look, as I said, in more detail next week on how we do that. Then you apply this different rotations with the angles, with CNOT gates. And then again, you encode or not. And finally, you measure. In classification tasks, you typically assign a label based on the sign of Z, or use multiple measurements for multi-class outputs. So even though the QNNs operate on exponentially large Hilbert spaces, their actual power is subject of research. So there's a reference, this is a list of references. If you go at the end of the file, there's a reference to Abbas, which introduced a notion of effective dimension and argue that some QNNs can outperform classical networks in terms of trainability and generalization. However, most of the nowadays, they actually don't show a clear, how to say, for quantum machine learning algorithms, what we might call a clear quantum advantage. So if you have a QNN, then with a given output, f of x of theta, and where you have the parameters theta you want to train, one of the typical functions which many of you have encountered is actually the standard mean squared error. So this follows, so the output which you have from a quantum neural network is typically a classical result. And then you would feed that one into the cost function, and this is a quantity you optimize. So what we would be doing is simply to compute the gradients of this function. So it's pretty similar to what you have with a standard neural network, except that the standard neural network, you're now replacing the hidden layers with a different set of gate operations. And these operations can be on all qubits or just a selected subset. Because then the circuit which you're setting up depends simply on how complex you make it. And you can make it as complex as you want. But keep in mind then that the more complex you make it, like you did in project number 1, there were people in project 1 who actually had pretty lengthy set of circuits, in the sense that you had many parameters you trained, so you did many rotations on the qubits. It gives you more flexibility, but it gives you also perhaps a less trainable model. So the typical example which we will also deal with is something like a variational classifier, a binary classifier that can output the Z0 and qubit 0 and predicts label +1 if this function f is larger than 0 and else -1. That's a typical example. So the QNN is implemented by layering this variational quantum circuit. It generalizes neural networks to quantum circuits, and then encoding maps classical features to quantum states via rotation gates, and the ansatz, variational layers, defines the network expressive power. So what I see I'm running a little bit out of time. What I'm going to do next week is to look more into the details of these different steps which you see here, of a simple feed-forward neural network. And we are going to look at examples with few qubits. And we're also going to look at examples on how we encode the data. And in the codes which you have here, normally the gradients are computed by the parameter shift rules, because for many gates, you can actually compute this quantity here, which is the same which you included in project 1. And if we just skip this one, where we will start next week is actually to look at some simple examples. So this information which you see here is the same you find in the slides. We are going to actually look at the simulation of a quantum neural network just using NumPy and PyTorch. And the gradients are obtained by the parameter shift rule, which we have for the VQE. And we are going to look at the regression problem first, and then later we are going to look at the classification problem. So this will be roughly the topic for next week, where we look into more details on how we can actually set up a quantum neural network. And then we will bring up the codes which you see here, but we are going to repeat a little bit of this, and then we will move into quantum physics-informed neural networks for solution of differential equations. So that's roughly the topic for next week. I wanted to spend some time today to link with the QAOA, because the QAOA is actually an example of a quantum neural network with a fixed unitary transformation. Whereas now, we have the flexibility of defining the hidden layers with as complex quantum circuits as we want. The more complex we make them, the deeper the network and the more parameters are trained. So instead of going into the codes now, because we're getting close to the end, I suggest that we stop here today. And then we spend next time on, in particular, how we encode the data. So if we go back a little bit here, the topics we are going to look at in more detail is simply how we set up a feed-forward QNN structure. And then we are going back to the codes and see how we can train them. And then if we get time, we will look into pins. And finally, the last lectures will deal with the quantum Boltzmann machines, if we get time. If we get stuck with the pins and quantum pins and neural networks, we will just stay with that. Okay, I'm going to stop the recording.